Hi, my name is Linnea.
I'm Bezia.
And I'm Linnea, and this is episode number 11. No, episode number 10 of the Lemma Journal Club.
What is the Lemma Journal Club?
Oh my God, way too loud.
Yeah, we'll see how that one goes. I really like this bit. I don't think it's worked once. Because one of two things goes wrong. One, I deliver it like that, and it's a total piece of garbage. Or two, the audio system that we feed this through to turn it into a podcast says, well, that is clearly wrong, and tries to fix it. So I don't
start our intro.
No. You're supposed to now describe.
The Lemma Journal Club is the show where we read every paper to tell you if you need to read it. You probably do.
Do you think people need to read this paper?
Sure, it's 2 minutes.
Yeah. We have a terrific paper for you today. It's a short paper. We are talking about the research paper, How the Venus Flytrap Snap. It's by Yoël Forterre, Jan Skotheim, Jacques Dumais and L. Maha. There's no picker or picky today.
You are the picker.
You, the listener,
you
are the
picker.
Listener. Sort of, right? Okay, so we put a vote up. We ran a couple weeks ago a fun draft where we invited people over and we're like, what is your team of the 5 or the 3 best papers? What's your dream team of 3 papers in a draft? And so you have a draft. The pool is all papers ever written. And people drafted 3 papers. Linnea scooped me on one of my papers, so I didn't get to pick it. And so we had a vote for everybody's first pick of that draft of what you wanted to listen to. And 8 people voted, because that's our listener base. 2 of which were us. Thank you for voting. There was essentially a tie, not including me and Linnea. And then me and Linnea voted as a block because the tie was between this paper and a paper that is incredibly long and dense and difficult that we will do sometime, but not today, because today we are so tired.
So tired. I can't string sentences together.
So we voted for the shorter paper.
Which is, I feel, like a paper about what one dreams scientists are. Like when you're a kid and you're like, oh, I'm going to grow up to be a scientist. This is what you think you're going to grow up to do. It's like the old English noblemen doing their little science experiments in their backyards because they find it interesting and that's what they want to do.
The paper is about how the Venus flytrap snaps so quickly in 100 milliseconds. And the summary of the paper is thin sheets are easy to bend, but hard to stretch, which I'll get into in a bit. And maybe I'll put a little clip of columns.
Yeah, we should definitely link to it.
Saying thin sheets are easy to bend, but hard to stretch. It was picked in the draft as Samita's number 1 pick. I asked her why she picked it. She had a good speech on why she picked it at the time, because you're supposed to convince people in the draft that your team is the best team. But her summary of why she picked it is essentially what you just said, that there's a lot of engineering, there's a lot of biology, there's a lot of physics, there's a lot of angles at which this is fun. And reading it made me think of a conversation that we had in my lab one day of what is biophysics. And, some people were like, oh, traditionally biophysics is biologically oriented, like structural chemistry, which is a weird heritage of the word that we really don't like.
Yeah,
And then other people, us would say, oh, it's the foundational principles of physics, but, entrenched in biology, because biology has some really unique rules of the game that aren't present in,
Yes, I like that definition
equilibrium
better.
systems. One person who studies venomous snakes in my lab was like, oh, I thought biophysics was like biomechanics, how the venom get out of the snake's teeth, right? And you make those physical measurements, right? And so in that sense of the word biophysics, How the Venus Flytrap Snaps is a biophysics paper of this kind of biomechanics, biology mechanics. What are the physics of the mechanics? It's like the first year undergrad classical mechanics applied to biology is what biophysics is in this sense.
And there's something really beautiful about it to me. When you can take a very a very simple knowledge of physics and apply it to a system that you've observed, it feels really nice and neat.
It's an interesting format. It's letters to nature. So this must be this micro format that nature has, where this is not a full paper. This is, it has to come in under 1,000 words and it has to fit on a page and a half or something. It looks a little bit different than what I think of as the
Looks a little old school, but it's 2005, so that makes sense.
2005 is what makes this paper so interesting to me.
Yeah.
Is that in 2005, there is some technology, right? So they do some high-speed microscopy. They do some 3D simulations where they're showing the stress.
I mean, microscopy is not true, right? It's just imaging. Yeah.
Photography. I'm sorry. But,
well, I'm just...
Yeah. But then they also have a lot of hand-drawn images in this paper. And I don't think it's a stylistic thing. I think they were how figure 2A, they just had to draw this thing by hand that we would now have many ways to show. Figure 2B, I think maybe the hand drawing is stylistic. It certainly scanned in to the journal very poorly. But it was interesting to see this amalgamation of technologies that was around in 2005 where they could really do some things and some computer simulations and they couldn't do other things yet.
Yeah.
Some of the figures are I would have done this instead of that. But it's from a format and a time so long ago that I'm not really willing to dive into why things are the way they are in this paper. So I guess I'm going to ask you some questions.
Great. I love questions.
What is a snap buckling instability?
I think it's what it sounds like.
It's a terrible answer.
A snap buckling instability is like these snap bracelets, right? That you played with as a child.
Okay.
So when you it starts as a straight rigid rod, and then when you flicked it, it would snap around your wrist.
Sure.
And that is due to a mechanical instability.
What's the snap and what's the buckle in the snap bracelet?
That's a good question. What's the snap and what's the buckle? Well, I think there's a buckling.
Snap is the change of the curvature,
and the buckling is the buckling of the whole
thing. So
bracelet
you've got narrow curvature and long curvature. The snap is the buckling of the narrow curvature, and the buckle is the rolling up of the whole curvature.
Yeah.
Okay, that's how the Venus flytrap snap. It's got two curvatures. It sits really close to that snap thing. It does a little bit of biochemistry that's unclear to do the short axis, and then it rolls up on the long axis, and then you're done. And it does it really fast.
Yeah. My question, how much of a mystery was this before?
I gotta assume
not at all. Yeah.
I don't know. The 2005, I don't know where this fits into the puzzle. Were people doing stuff like this all the time? Did everyone know this stuff like the back of their hand?
Yeah, it just seems like if I've never seen a Venus flytrap in person. Have you seen one in person?
Yeah.
Oh, yeah?
Yeah.
Okay. Have you poked the little thing? Is it clear to you that it's the same sort of material as a snap bracelet?
The Venus flytraps that I have encountered, I mean, maybe they weren't proper Venus flytraps, would close very slowly.
Well, that seems like
I was always a little bit surprised that they were able to catch any food because of how slowly they closed.
I mean, just looking at this, figure 1A, right? I'm I think if I looked at that and I touched it with my hand, even if I had killed the plant or something so it couldn't snap itself, I would be able to tell that was a snap bracelet.
Yeah, and so in fact, they say that's what they do in the paper.
Yeah.
They say, by squeezing the leaves with our fingers, we were able to induce a snap transition mechanically, indicating that the leaf was indeed in a bistable configuration. So yeah.
So they're just doing the physics behind it for the fun of it,
the physics that they're doing is pretty. There's also clearly
mechanics behind it. Yeah,
the physics is unit analysis that they then test through measurements, which is cool. I sat in on some courses that Maha taught, and his bread and butter at the beginning of these courses was hey, you can do a tremendous amount via unit analysis, and you should, and let's do something fancy via unit analysis. So this paper. The physics is almost entirely unit analysis followed by a measurement.
Yeah.
Which is cool.
Yeah. And then the biology part is that it seems they don't seem to be willing to make a strong claim in this regard, but their model and the data suggest that the plant is sitting right next to this instability.
Which again seems obvious, but there's they say, our kinematic and mechanical measurements allow us to identify two distinct pieces in the puzzle of trap snapping, an active biochemical component and a passive elastic component. Upon simulation, the plant actively changes one of its principal natural curvatures. the microscopic mechanism for which remains poorly understood.
And so I did try and go find what, 2005, that was a while ago. That was 20 years ago. What's been learned about the biochemical mechanism of this? And it seems like not much based off of my perusal of Google Scholar.
The hype and funding for how the Venus flytrap snap was not sufficient to carry it through to the next decade.
Yeah, or the results on the biochemistry side were not as snappy.
Exciting.
Yeah,
it's not as snappy. That's good.
But yeah, one thing that I was confused about in this paper is they talk about that it's necessary for there to be fluid for the damping to get the timescales to line up, and this felt. I mean, I didn't understand, what the fluid was doing in the damping. It's somehow. Yeah. And then B, it seems very hand wavy to be like, our time scale didn't match up with our theory, so we introduced a fluid damping.
I also didn't understand, why does it have to damp? Why does it damp?
Why does, biologically, why does it damp?
Yeah, they say, biologically it's necessary for this thing to damp, otherwise it's not going to successfully catch the fly. But when I'm trying to kill a fly with my hands, I don't make sure to slow my hands down just a little bit at the very end of the clap. That's never been a successful strategy for me.
Well, they said that there's a trade-off between how quickly you go through this fast transition and how long it takes to actuate that transition. I thought this was this alpha parameter.
I thought the larger you were, both the easier it is to start the transition and the faster the transition goes, was my understanding. Is that the opposite of your understanding? Okay, so figure 4, alpha. As alpha goes up, so we just, try to plot time delay versus omega max, which is the max angular velocity. So yeah, the max angular velocity also leads with the largest delay to snapping. So you're right.
So you have to the leaf has to sense that there's a fly and be able to snap quickly around it.
Yeah. And
there's a trade-off.
Okay.
And that's this alpha C equals 1.
Sure, but what did that have to do with why damping is necessary?
I thought that was somehow a way to tune alpha. Maybe.
Interesting. The time delay between the beginning of the motion and the snap increases with the parameter alpha, as does the maximum speed of snapping. Gugh. This is probably because the delay reflects the time required to cross the stretching barrier, suggesting that leaves are poised at the transition between smooth closing and snapping. That explained nothing.
Yeah, it doesn't explain where the fluid comes in.
The actual speed of snapping is a critical parameter for trap function.
Yeah, sorry, this is turning into a bit of a journal pub where I'm trying to find the fluid. I forget where it was mentioned.
Oh, it's right where I'm reading. I could just keep reading. We conclude that the internal effects are not relevant in setting the timescale of motion. Furthermore, on comparing the elastic force acting on the leaf to the force due to the motion through the external air, we see that some stuff, hence the damping must occur internally, because the leaf is highly hydrated. Because the leaf is highly hydrated, a natural candidate for damping is provided by the flow of interstitial water through the surrounding elastic tissue. The curvature change during closure induces a transient flow perpendicular to the leaf surface, which occurs over some time scale.
I don't see where they're saying here that the fluid is necessary for the snapping.
They say that they don't observe ringing and that air resistance isn't enough to create the damping.
Yeah.
Hence, the damping must occur internally.
Sure. But I thought this whole conversation started because you asked a question.
My question,
yeah,
which we're still not talking about,
okay, is
why does the thing damp at all?
Why does it damp at all?
Yeah, why not just smack shut with maximum velocity?
But that's what I'm saying is maybe it's not purposefully damping. It's damping as a consequence of the fact that it is a fluid or it has fluid inside of it.
They say, and I quote, the rapid damping that is equally crucial for efficient prey capture.
Rapid damping.
So this is essentially the last paragraph of the paper, right before the methods. Smack dab in the middle of the paper. They say, once this change occurs, the geometry of the doubly curved leaf provides the mechanism by which elastic energy is both stored and released. And the hydrated nature of the leaf induces the rapid damping that is equally crucial for efficient prey capture. This ingenious solution to the problem of scaling up movements and speed from the cellular to the organ level in plants, nature's consummate hydraulic engineers, shows how controlling elastic instabilities in geometrically slender objects provides an alternative to the more common muscle-powered movements in animals.
Okay. Yeah.
So
Sorry, I
why-
missed this phrase.
Yeah. It's one of like 3 phrases in the paper where I'm like, is that a typo?
I just thought that the fluid that they observed that there was damping, and so they put a fluid in. And I didn't understand. I didn't follow that there was an argument saying that this fluid damping was important, other than that it was necessary for these to capture the 3 phases of snapping that they observe in experiments. So
Yeah. So my question is, now given that, why is the damping critical? Or why is the damping? That's not a critical damping. That's a bad choice of words. Why is the damping important?
yeah. So I mean, I guess like, do you think it's because it or like that having these 3 phases is important? Having a slow, fast, slow phase?
I don't see, if your objective is to kill flies, how having a slow moment right before you kill the fly is useful.
Yeah, I don't have an answer for you. I'm sorry.
Do you think if I try to start, I'm pretty good at killing flies with my hands. Do you think if I start slowing down just the moment before I close my hands, that's going to work?
No.
Yeah, I don't either. I'm going to try it though. Just
Well,
for science.
maybe if you hydrated your hands ahead of time.
What does turgor mean?
Turgor is plant cells are under turgor pressure. There's like an internal pressure, water pressure that pushes out on the cell walls.
I've started to notice that Wikipedia has a nasty habit of defining the Wikipedia thing I looked up in the first sentence using its own word. So turgor, if I look up on Wikipedia, it's going to be like, turgor is the turgor pressure that plants have. What does turgor mean without the word turgor?
Turgor pressure is the internal pressure inside plant cells
Due to
I think, water.
So turgor pressure is osmotic pressure?
Sure, we could call it osmotic pressure.
Or can like...
I don't know what's driving. You're asking what's driving the turgor pressure?
Or my other option is that like plants can pressurize, like they're little water guns growing out of the ground.
Yeah, I think that's the way to think of them.
Plants can pressurize themselves?
That they are like, that's how they stand up, right? Is that each little cell has hard cell walls and they fill the cell to its maximum to hold itself up. And this is why a dehydrated plant sags, is it's losing turgor pressure.
In editing these journal clubs, I have a lot of verbal things that I do when talking to someone to acknowledge that I'm listening to them, that I'm hearing them, that I'm acknowledging them. One of them is Zvonimir's famous which I have unfortunately adopted. Or a yeah. But in a podcast format, it is so obnoxious because it's my little audio way of going, on top of your actual audio that we're trying to look at.
I mean, maybe we should get little mute buttons.
Okay, so I have little mute buttons over here.
Yeah.
Look at all my little mute buttons. I'm petrified to touch any of these mute buttons because what is inevitably going to happen, because we don't have headphones on these because we're amateurs.
Yes, to release
I'm
it
going
at the
to
wrong time and
mute-
clip. Yeah.
And then it's going to stay muted for 20 minutes before I notice it. So if I
It's
could...
got to be an active mute, like where you
Oh,
hold
you
it.
hold the mute.
Yeah.
Gavin was talking about how he had a pedal,
Yeah.
that he has a mute pedal that he could hold down with his foot. We could install some mute pedals.
Yeah. Seems like a great use of time.
Look, I feel like every time any scientist learns that I am doing anything other than the major project, which right now, I'm in review. I'm not starting another major project while I'm in like my 3rd revision or whatever. But even then, this sense that anytime that I admit to doing anything other than the main project that I'm supposed to be doing, I'm seen as unproductive and lazy and scattered. And it's very frustrating these days to not be allowed to work on anything other than the one thing that people have you pinned on. Sorry, that's my little rant.
Yeah, I had my career meeting with Martin this week, and I was like, yeah, one thing that I would enjoy is having more collaborations in the lab. And so if you see overlaps, and he was like, oh, your time is so precious and you're already so pulled in so many different directions. And I was like, well, time is,
Elastic.
Yeah. And I don't
what
think
you
it's going to
get-
make me less productive to be working on other projects.
I feel like
it's,
somehow the generation above us does not have this, that like when I talk about like, oh, if I'm obsessed about something and like excited and working with someone exciting, I will do more in 5 days than I will do in 3 years. If I am grinding something out, it's going to go slowly.
Yeah.
And people don't seem to appreciate the importance of joy and diversity in work.
I think people appreciate it. They forget.
They forget.
Yeah.
I'm just bad at reminding them. I spent Thanksgiving making a little test database, not really a database, but a test collection of experimental images that I had a lot of fun making. It was a blast. I thought about the logistics of putting it on the internet for everybody to see. And I think the short version of this is that nobody will ever see this website. But at one point, I went on to like Elsevier and Springer and all these publication companies, and I went to each individual paper that I was getting the data from. And on each individual paper, I found out there's a tools that you can click on. And on the tools, you can say, I want to request reuse permission for this figure. So you click that tool, and two things happen. One is it gives you the license that already exists, which sometimes for some of these things is a Creative Commons license, and you can use it already. And it seemed to be surprisingly random what journals had Creative Commons licenses of some sort already and which ones didn't. Like, it wasn't necessarily tied to what journal was open access, which I was really surprised by. But the point is, for the vast majority of journals, you get moved to the same system. There's like one company in the world which is going to be the middleman for you. Oh, you want to take a figure from this image? How much are you going to pay us? And I put, for the sake of argument, I'm a nonprofit company, let's say. How much do you think it costs to use one figure one time as a nonprofit website?
I want to say like $5.
Yeah, that would have been, I think if it was $5, I would have felt that was reasonable. I still couldn't have done it because I needed 40,000 images. So, any dollars was out of the question.
Yeah.
But $5, I think, that's a number, right? It was somewhere between $250 and $500, depending on how the specifics, how I filled out the form. And
That's
who's
crazy.
Getting that money? I
assume the journal and the middleman.
The journal and the middleman, but not the person who actually created and uploaded the image.
Yeah, they paid to put that image up, right? Okay, so you could go straight to the author and say, look, I can't just pull this from your paper because... Yeah. But that's a whole pain.
So what do these middlemen think that they're doing, charging $250 for one copy of one figure? It's an insane button. It's like a whole menu system. Like, somebody's actually paying this stuff. I was blown away.
Yeah, I don't know who's paying that. I don't understand, because I feel like most use cases... people are just pulling, you can buy the paper. If you're not at a university, you can straight out buy a single paper from Elsevier for $40, right?
Yeah, which is still pretty bad, but
it's still way too much, right? And I would never do it. But you buy the paper from Elsevier, and then you would have all the figures. And I know technically you wouldn't have the right to put it up on a website, but are they going around and suing people for this? What's enforcement here?
Yeah, I do. I was for this thing, I'm not going to continue on this because for a bunch of reasons. But I think in general, there is in science, we're over concerned with the rules where no company, nobody in Silicon Valley is remotely concerned with the rules.
Yeah.
And then we're also
talking to our friend who was the license, the default license on GitHub is actually really aggressive.
And we just ignore it.
And we just ignore it, right? Because nobody goes through and picks the non-default Creative Commons license, but we all share the code anyways. And companies do this as well. And it's just that somebody would have to notice.
Because scientists are the ones who should be sharing and who should be open. And scientists are the ones who are trying to spread information around the community. And we are the most tiptoey about freely sharing information and freely using each other's stuff.
I think again, it's because we're too emotionally tied up in our work.
I think it's because I think it's because we're just naturally scared people.
But also because in our day-to-day life, anyways, we're way off topic, but
well, okay, coming back to topic, we talked to Maha once about some experiments we were doing in Arabidopsis, which we thought were really cool experiments. And Maha was essentially Arabidopsis is a really boring organism. Why don't you do something more exciting? And I think I don't think that's what killed us from doing that project, but it's one of the few things that we were I guess we're not interested in this project. Screw it. Do you think that Maha would now be excited about a similar project in the Venus Flytrap? Or do you think it has to be a new organism every time, that it's got to be a new thing? Do you think the excitement is in not Arabidopsis, or that the excitement is in new thing?
I think not Arabidopsis, but I think Yeah, like a new motif is what he's interested in, right? He's a theorist, so he's looking to explain things that, look different than what he expected them to.
And that means new models as well. It's not just new ways of thinking about old models, but it's new models.
I think for Maha, yeah, but I'm not sure. I think also, I think eventually he would have been excited about this plant root project.
So I think the other thing that's worth talking about is thin sheets are easy to bend but hard to stretch.
Colm Keller.
One of the best scientific communicators I have met in science. Geez, I hope you're not listening to this. Colm is the person who taught me how to do audio recording at NYU's Doppler effect radio show. There are our NYU radio science show. Colm went on to do a bunch of like TED Talk animated shorts during his PhD. And one of them was about how a shape like a Venus flytrap trap or a potato chip or a flat piece of paper or really particularly a pizza would have its material geometries constrained depending on how it was folded. And his catchphrase was, thin sheets are easy to bend, but hard to stretch, which I think is pretty obvious if you take a piece of paper. A piece of paper is easy to bend and easy to fold, but very hard to stretch. And Colm basically said, look, if you have a piece of paper and you hold it by one end, it flops over. If you fold it, you don't have to like crease it, but if you just kind of fold it a little bit and hold it at one end, it won't flop over. And why did that happen? Well, if you folded it from one end and it was to fold over, it would inherently change its shape. It would no longer be a flat piece of paper. It would be more like a potato chip. And a potato chip and a flat piece of paper are not isomorphic. Colm says aren't isomorphic in his
Irish
video. And it's such a great aren't. That's one of my, I think, the greatest science videos that I've ever seen. And that in order to go from a flat piece of paper to a potato chip shape, you must stretch the material in order to transition from one shape to the other. And so I think the idea here is the reason why there's so much energy built up in here from one configuration, this snap, is that you have some almost stretched or like stretched system that is costing a lot of energy because thin sheets are hard to stretch. You make a small geometric change, and all of a sudden the thing is allowed to fold into this new potato shape. It can unstretch and it can come really quickly down to this new position. Do you think that was an appropriate?
Yeah, I think that was great. I would highly recommend people go watch the video about why you fold your pizza.
I'll link to it here. Yeah, the video is why New Yorkers fold their pizza, which is a great.
But one thing I wanted to say about the paper before we sign off.
I'm not signing off. I got to talk about folding pizza.
Didn't we not?
We did, but I want to just say something about folding pizza. My whole life, right? I've gone, walking back from classes, folding a pizza as I head back to my apartment or something, right? I have been watching the opening scene to Saturday Night Fever over and over and over again. I don't know why, but there's something about the cinema of that scene that just gets me.
John Travolta, when he gets a pizza, he gets two pizzas. He's in Brooklyn. He grabs two pizzas and he does it and he kind of like pseudo folds the two of them. But every time I see that scene, the same thing occurs to me, which is okay, one strategy is fold the pizza. Second strategy, don't make it a thin sheet. Just stack the sheets, and now it's also good. I don't think I've ever seen a real person outside of that Saturday Night Fever opening scene eat a pizza by stacking multiple slices on top of each other and biting through the multiple slices like it's a lasagna. Look, it's a page and a half paper. We got to say something. The thing I wanted to say about the paper is, did you read the methods about how they made the strain field measurements?
Oh, I didn't. I actually should have read. I normally am I've been reading this paper for so long, I'm not going to read the methods. I should have read the methods. It's like a one paragraph of methods. I could have done it. All right, strain field measurements.
The strain field measurements, what they did is they take little casts of the fly trap before and after.
This seems super unnecessary.
Yeah, to get the strain field.
Why?
And I was like, why? Like, can you not get this from the dots?
Using a non-invasive replica technique. 19. Scanning electron microgrowth sequences from individual growing misderms before, during, and after the transition to flowering. I don't know. Scanning electron micrographs sounds pretty invasive to me.
But they take molds of outer... I think they're just citing the paper that they must have done this at some point in that paper. But they take molds of the outer and inner surfaces of 6 different leaves before and after the closure.
Oh, look at this. This is what I was looking for when I was reading the paper, actually. I really should have read through these methods. Under elastic shell statics, they have the equation. This is the equation, the energy of bending plus energy of stretching. This is the thin sheets are easy to bend but hard to stretch.
Yeah, they have that in the main text.
Do they? I was looking for it.
It's at top of the last page.
They have this, but I thought they just had this, right?
Oh, you want the full thing. Yeah.
This is the abbreviated, maybe this is also abbreviated. The thing that I want always with this thing is that its thin sheets are necessary. And here it also looks like,
No, but alpha is the thin sheets.
Yeah, you're
necessary.
right. They had it in the main text. I was happy and then I moved on. I didn't highlight anything in red in this section. So I
highlighted this in yellow as like the main point of the paper.
Oh, yeah. Yeah, that's a good thing to highlight in yellow. I should have done that. I highlighted green for me is the main part of the paper, and I highlighted suggesting that leaves are poised at the transition between smooth closing and snapping.
Okay, yeah, that's another main point. Yeah, I just liked that that's how they made the measurement. I thought all of these, it's 2005, which is such a weird time because it's long ago, but it's not that long ago.
But I think
all of the experimental measurements feel so in your basement.
Yeah, I think it is like develop film at the local store time period.
2005? Yeah, maybe we were still doing film.
I don't think people had smartphones. You could take a photo with your phone.
I think you had digital cameras.
Yeah.
And they have a fast, super fast, the same Phantom camera.
So when our PhD advisor was talking about developing film for his experiments, what year was that?
I think that was a little bit before, right?
I don't know. No.
I don't know. Yeah. Maybe the highest sensitivity cameras were still film.
Yeah, that seems possible.
Yeah.
Okay, we've successfully vamped for 42 minutes on an extremely short paper.
Okay.
I guess there's supposed to be some actual like sign out things.
Oh yeah.
Yeah.
Do we want to do?
If you could have added one thing to this paper, what would you be adding?
The thing that I left the paper wanting to know, right, is okay, the mechanics to me felt intuitive, and I know it's they're intuitive because we know it now. But I wanted to know, what's happening on the biochemical, on the plant side to induce the curvature change in the X direction.
Yeah, absolutely. But then what experiment can you do?
Yeah. So I tried to look up what's happened in the meantime. And it seems like not much. I don't think Venus flytraps have much genetic tractability still. And maybe I just missed it. And I'm not sure what the right experiment is to do there. Did you ask me for a specific experiment? Or
I asked you for a specific... I guess I said if you could add one thing to the paper, so I guess not. But I think the way to go about this is trying to recreate the system in vitro, quote unquote, or like a cell culture system of the molecular snap, I think is what you want.
Yeah.
Can you make a snap bracelet based off of a small collection of cells?
Yeah, or you start, taking things out of the system, right? If you have genetic tools, you say, let's knock down some of these signaling. So there was a paper that did some calcium imaging, calcium signaling imaging.
Cool. Calcium. I shouldn't be so dismissive of calcium signaling. It's just that's a thing to do.
And it does seem to be that there's, unsurprisingly for something that's happening fast, calcium is involved.
Yeah. This is why I say block is you know what you're going to get before you do it. But it's
good to know. And so then you can follow that pathway, right? And you say, what proteins are here that are responding to calcium and what's actually going on. And so that's what I want to add.
I guess the whole point here is that it's not energetically costly or minally energetically
costly. It's minimally, yeah. It should just be a small...
So I don't think watching the ATP is going to be super exciting here.
Yeah. Which is cool, right?
Yeah. Do we want to do a summary for ASIA? We didn't really pick this paper. I feel like normally these ASIA outros are really about us as human beings and who we are on a deep level.
I don't think we...
Yeah,
to do
honestly,
it
this
today.
is not a paper that we picked as our top papers. I think it was a good pick.
It's a good pick. It's a good paper for listeners. Again, for listeners who are learning how to read scientific papers or who are just like trying to get more out of the podcast. If you're spending your time listening to it, this is a good one to read and engage a little bit with. Because
Yeah, it's good that you did that at the very, very end, 45 minutes into the recording. So that. So I guess we'll every 5 episodes probably do a vote. So I'll probably put the next vote up next week, and I'll make people aware of that. It seems like most people don't like to use Patreon, so maybe we'll try to vote on a different platform. Maybe we'll try to see if YouTube has a voting tool, as a lot of people seem to be engaging through YouTube. And I'm not sure if we'll do the same papers as before and then just remove how the Venus flytrap snaps and throw in one more new option, or if we'll do all new options from that draft. But I think we'll do 5 more options from that draft. And yeah, we hope that you enjoyed our very tired episode. We've been trying to get ahead in these recordings because we don't want to miss one, but life is getting real rough for us right now. So these are going to get more tired and more incoherent as we move along.
No, we'll bounce back.
We'll bounce back, but I think like mid-January. So there's going to be like 3 to 4 pretty...
Yeah, maybe we should put in some really solid like questions and stuff to ask
really
each other, so
formats.
we can lean back on that when our brains aren't 100%.
Yeah, if you've got paper suggestions, if you've got format suggestions, if you've got feedback, mean or nice, we love it. And I think that's it. You want to say your bye that you always leave on? You have a very characteristic bye.
Bye.